Designing and analyzing the L-band horn antenna. Creating the waveguide. To form the waveguide section of the horn antenna, we will create a cuboid using the second definition method. The default dimensions are adjusted accordingly using mathematical expressions as shown in the video. Then I have clicked the create button. Then moving on to the constructing the horn flare. Next we create the flare section of the horn. Start with defining the base center. Holding Ctrl plus Shift allows us to snap the origin to the face center of the cuboid. We then snap to the two edges of the cuboids to set the bottom width and bottom depth while the remaining dimensions are entered manually. After setting these parameters, create the flare and zoom to extents. To ensure proper meshing, we need to combine the different components. Select all parts in the model tree and under the construction tab, we click the union tab. The horn aperture remains closed at this stage, so we select the indicated face and delete it. Similarly, remove the face at the junction between the waveguide and the flare. Then moving on, defining source and excitation. Since no additional transformations are needed, we skip the transform tab and proceed to the source load tab. The antenna will be excited using a waveguide pot. Rotate the horn so that its back face is visible. Then select the waveguide's back face in the 3D view and click create. Add the waveguide excitation by selecting the corresponding option. We only require the fundamental mode, so we leave the default settings unchanged. To ensure the isometric weave, use the relevant icon in the weave tab. Next we define the operating frequency. In the source load tab, click frequency and set a value of 1.645 GHz. As I have clicked in the video. Then select OK button. Next, moving on, setting output request. Now we configure the output request. Under the request tab, select the near fields and choose a Cartesian coordinate system to evaluate the fields within the horn aperture. Specify the start and end coordinates along with the number of field points as shown in the video. As I have shown in the video, I have entered all the field points, the number of field points, the status and coordinates as well. After clicking this, click the create button. Additionally, request for field analysis. Select 3D pattern for a quick setup and click create. If needed, hide field request by right clicking on them and selecting show or hide. Optimizing the computational resources. I have shown the show or hide selection. Then moving on to the optimizing the computational resources. For antennas like this horn, which are several wavelengths in size, computational efficiency can be improved using HOBF. Look, HOBF. Enable these options as indicated. Next, moving on, meshing the model. On mesh menu, click the automating meshing, and CAD feko automatically generates the mesh based on the wavelet. Next, running the simulation. To execute the simulation, navigate to the solve or run tab and run feko. The solver provides real-time output during the computation process. Any errors or warnings must be resolved by returning the CAD feko for corrections. Then once the simulation is complete, the post feko is used for post processing. As I have shown in the video, I have used the post feko for post processing. Next, visualizing the results. To analyze the results, go to the home tab and select near fields. Then choose near field 1 to visualize the near field distribution within the horn aperture. For far fields analysis, select the graph types as Cartesian, then click far field 1. To wrap the graph, use the theta wrap option in the result palette. For additional visualization, duplicate and change the fire angle to 90 degree to compare different cuts. To convert the graph to dB scale, select both traces and apply the dB transformation. To generate a polar graph, navigate to the display tab and choose the polar copy.